Thank you. So to get this started, I wonder how many of you are actually involved right now in deploying or developing ML models where there is an end user? I don't care if the end user pays or not, but how many of you are involved with that? Okay, great. And how many of you have been at one of the excellent sessions in the last 2 days about explainability or interoperability? Okay, just a few. So for you guys, some of what I say might be a repetition, but I'll try to skim through it. Okay, I'll make you 2 promises. One, if you're interested in explainability, I'll show you some cool tricks that you can actually apply to use explainability to make your model better. That is not just to understand it, but actually make it better. The second one, I'm going to finish ahead of time. Okay? Great. Thank you. I knew that's always a clincher. Okay. So just a few words that are mandatory about NEC, since we're not that well known in some parts of the world. So NEC was a startup a while ago. The guy on the left, who looks Asian, he was the founder, and he worked at another startup where you see him now, founded by a guy called Thomas Alva Edison, which I hear was quite successful. And that was 120 years ago. So this summer we celebrated 120 years in operation. We've always been doing a lot of research. I'm not going to bother you with the non-AI stuff, though we do build spacecraft that go to asteroids with AI. But I will mention another thing which some of you may have heard about. There was a young researcher in NEC Princeton Labs in 2003. That's about 10 years before ImageNet paper, if any of you know about that. And he had this idea to apply convolutional neural networks to detect people in video. You can actually find this video in YouTube. The researchers look much older now, but they're still around. And that person was Yann LeCun. You may have heard that name. He's also done quite well for himself. He recently won the Turing Award. So AI, and the point I'm trying to make is AI was here and was being used, including convolutional networks and what you may call deep networks, well before it became such a hype. And that's why you get to learn where it works and where it doesn't, and why. Okay. So at NEC, we try to apply AI into areas where there are some customers, okay? Now, a few things about customers, and I wonder if someone here strongly, vehemently disagrees, please do speak up because I want this to be interactive. So first, customers don't really care about state of the art or the area under the curve or the ROC. I don't mean they don't care about it at all. I mean they want to see how it relates to their actual data in production. To give a very simple example, maybe you trained some sophisticated image classification engine on 2 million images from the open internet and another million you even got from the customer, and it's all great, and you get really nice curve and well above what you expected, and then you deploy it. And on the first day, it is shown 10 pictures of ducks and says, this is a battle cruiser. Your customer is not going to be happy. And you're going to tell them, and I see people, I hope you have not been in that too many cases, but yes, it's like that. Now, does it mean that the customer is silly and they don't understand what statistically meaningful samples are? Well, actually, they do. That's not a problem, and we'll say what the problem is later. Second thing is, there's never enough training data of the kind you really want, right? I mean, like, there's plenty of boring data, but then there's the anomalies, and they happen to be rare. If you're in autonomous driving, you don't get that many cases of 2 buses colliding in the middle of the junction, right? It just doesn't happen so much, and people are reluctant to try and reproduce it for you, okay? In healthcare, medical, it's like, having been involved with it now, is you see those extreme cases. Each case like that may be actually a medical paper, but they're extremely rare. They're very important and they're very rare. If you say, I will only incorporate this into my model once I have 100 or 500 samples, well, that's forever. So that's the second problem. And the one that's harder to quantify, but is very important, is they want the AI usually to be like us, not smarter than us, but as good as the best people, experts, subject matter experts we have at the area. Meaning, what does it mean like us? Well, first of all, there are ambiguous cases where people don't agree. Then it's quite okay that the AI doesn't always get it right. But there are the trivial cases, the ones that differentiate the experts from the beginners, and they definitely expect the AI to do as well as the experts and not to do beginner mistakes. When you talk about healthcare, for example, you make a beginner's mistake, they lose even one, they get antsy, okay? So before we talk about the practical sides of explainability, how did it all come about? So AI use in the last 7 years, the two main precursors were one, a financial success in the market, and the other one, a scientific one. The scientific one was ImageNet, where I'm sure many of you have heard. AI can be trained with deep networks to do far better than any algorithm before in image recognition. And some people claim it's better than people in some sense. I don't think that's true. The main reason that seems to be the case is because in the ImageNet today they have 1,000 classes where they have different kinds of ships and different kinds of planes, and people might make a mistake between them. But not even a 4-year-old child will mistake a ship for a duck, and the ImageNet AI does sometimes, okay? So it just does. Okay? The other thing AI does extremely well, and that's an even bigger engine, is it makes money. It makes money for the internet companies in things like recommendation engines and advertising. And there, it's very simple. If you can get a better over day-to-day performance, meaning more clicks or more successful recommendations, nobody cares how the AI works, as long as it works, right? And the good thing about AI is that it can train to adaptable circumstances. People who were looking for one movie star a year ago, now they're looking for another. They write his name or her name in a funny way. The AI adapts to all of that automatically. You don't have to have people monitoring the news all the time and figuring it out. It's great, but no one has any idea how it works, and it makes more money. And that's one of the reasons, I suspect, that the big AI, internet companies always say you don't need to understand AI, because they might be a little surprised or unhappy about what happens when you open the hood, okay? So without taking a stance here, because that's not my area, there are people now that have started examining these algorithms and find what they claim is bias or other things, where some kinds of people get the good advertisements for the good jobs and the good opportunities, and others get laser surgery to remove some parts of your body and things like that. I don't know if that's true, but basically people are starting to ask themselves, is just hit rate, meaning like it makes more clicks, the only thing you should look at? Now let's get to more serious matters. If you talk about mobility, autonomous cars, many people are saying if they seem to be better than regular drivers in percents of accidents, that's good enough. Well, not quite. First of all, it's new. We don't understand how it works, which means we don't know really what we should test for to show that it really works well. Let me give you a simple theoretical example. After a lot of testing, these cars are rolled out, and Mount St. Helens in Washington State erupts again, as it did about 20 plus years ago, and suddenly you have this fine ash in the air, and maybe no one thought about simulating that particular effect at night when you're driving, and suddenly all your autonomous cars behave very badly. No one saw it coming because no one thought this would have that effect. Human drivers may still also make driving mistakes, but if they see it's too hard, they just stop, okay? So the regulator is considering what to do about that. It's a big issue. What you don't understand is very hard to deploy in that case. And maybe the classic example is medical diagnostics. At the end of the day, it doesn't matter if you call it a decision support system or a system to replace the physician or anything in the middle. A 55-year-old male, heavy smoker, comes to your clinic. You do the 3D CT of the lungs, the chest, and you find what is a nodule. It's a big one. It's a lump. Now you have to decide if you do a biopsy or not. Now, it so happens biopsies not only cost money, there's about 1 to 2% chance that they may cause further complications, as some of these people who come are not doing very well in the first place. And now you have to put that in the hands of AI. It's a tough decision, okay? So, as it may be no surprise to you, explainable AI is a big hot topic. I think there were at least 3 or 4 sessions about it, including one tomorrow. There was a wonderful training session by IBM Research yesterday. If any got to be there, or you can find it on the net, I really recommend it. They did a very thorough review of the whole area. And it's going to become a bigger and bigger concept, especially when you have to apply it to the left-hand side, okay? So that's a good basic criteria. If your AI is applied on very minor things, where only the aggregate, the statistically meaningful aggregate, plays a role, then maybe you don't really need to understand it so much, okay? So if it's showing you an advertisement or playing a tune on Spotify and it's not to your liking, well, no harm done. If statistically it works better, then it's probably a good idea. But whenever a single decision has a large implication on value or lives, it's a problem, Okay, these are the areas where you see that AI explanations are more sought after. Just to show you that this is not just hype or talk, okay? Two very real examples from the last half a year, okay? People have started applying and training AI for medical. So on the left-hand side, what you see, I hope from your distance the resolution is good enough, melanoma detection in skin, okay? So physicians, MDs, trained an AI module, which did well, and then it was applied in a different part of the country or even a different country where they use, and that's a very common technique, they use blue markers to mark where the suspected melanoma is. Why? Because many people like me have many spots, and if you just show a picture of the whole area, they will not be sure which is the spot the physician is referring to. So you see those two upper and lower blue marks. They were made by the MD or the technician as they were making the image. However, no one told the AI that this is being used like that in some areas. So when it sees that, it's malignant. You know, go immediately and have it removed. Then you zoom in again, and again it's benign. It's all okay, you can go home. So it's not that the AI was foolish. No one ever thought that this would affect it and that this procedure is used in some areas. Otherwise, they would have incorporated it, okay? So that's a very visual example why you need to be careful. Doctors, by the way, physicians, even if you never told them about it, if they see some blue marks, they may not understand it, but they definitely will not say clearly a melanoma because they've never seen anything blue on people, okay? Maybe they should, but they haven't. On the right-hand side, you see an NLP, natural language processing example, where surprisingly enough, a lot of the AI applications in medical right now are just extracting data from written reports. That is, physicians fill out long reports in their own language, and you have just to answer some simple questions about it. Not predictions, but like, did this patient undergo treatment A, and was it successful or not? That's it. So things actually, a nurse that's been working in the hospital for a few years already knows how to do. But the problem is you ask, it's not structured data, meaning you need to convert this unstructured to structured data. You talk to the GM of a big hospital and ask them, you know, can you tell me a simple thing? How many people this year at your hospital have undergone treatment for liver cancer? Seems like a simple enough question. They have no simple way to answer. They need someone to go over all the reports and for which mark a tick. This was liver cancer treatment or not. So the AI here is important. So people in a Seattle hospital marked a large corpus of text for the AI to identify whether someone underwent a very specific medical procedure. That's all. And they got excellent results. And then they went to a totally different place, Kansas City. And they applied it, and they got really bad results. Can anyone figure out why? They did good work. Absolutely, but let's say it even more strongly. The physicians were not the same people. That's all. You know, at the end of the day, in oncology, you may have in a good hospital 4 or 5 subject matter experts who write these reports, and they just use certain phrasing. They don't make it intentionally complicated. They use their language. And the 4 or 5 people in Kansas were just different, okay? So what I'm trying to get at is, if you don't understand your AI at all, a serious and justified concern of the customer would be AUC or ROC stability, meaning, yeah, it's really working well now here. I've seen what you've shown me. Now I'm going to apply it at my place, or I'm going to apply it again in my place, but in a year, will it still be the same AUC or ROC? Now remember, as data scientists, when we want to measure the statistical performance of our system on the label data, we usually have tens of thousands of examples or millions. It's very easy to get a statistically significant result, right? Because you do your chi-tests and everything, it's all great. But now when you're in production in a hospital, luckily for all of us, you don't get 200 new cancer patients a day. You get far fewer. So only after a very long time, if your ROC or AUC deteriorated, you will only be able to realize it statistically after a very long time, years maybe. And that's really bad. So the concern is not that the AI is complex and we don't understand. The concern is, can you assure us it will work just like it did in the lab? And that's hard to do sometimes. There's other things that make customers irate. One, for example, as I said, is making the stupid mistakes, right? I mean, like, if you make a mistake that only experts know how to avoid, they may live with that because they say, I don't have experts at hand all the time, I have to live with it. But if you make very banal mistakes, that's the problem. Another one is the distribution of errors. If you employ people, usually the performance day of the day, especially when you have a large team, is kind of constant. Maybe not the day after Christmas, but kind of constant. But if your AI suddenly, something minute changes and it gets really bad, then you have a big problem. You have no one to replace, right? I mean, like, if John is sick today and he says, you know, I can't do the work, you have others. But what do you do if your AI is sick today? And the examples, I'm not sure if you're aware of, but these are examples of what's known as adversarial attacks, which are very minute changes that you can inject into the input image. And on the lower image, actually cause the panda to be identified as something else. And then the upper image, it just causes the object detection to detect 1,000 bogus objects, which just crashes the software, okay? And it's not so hard to do these things in real life as well. Okay, so unfortunately, as in many things, defense organizations were ahead of everyone in predicting what this may be. So this is by DARPA, but it's not classified. It's just an understanding. They were trying to say, okay, some models are easier. Like, okay, deep learning is really hard, and we don't understand it. But as you can see here, decision trees, that's easy enough, right? You just apply a few rules, you follow the guides, and that's how people think that should be okay. Well, here's a decision tree. It was made by Jeff Hinton and his team. And what it does classification of handwritten digits, okay? Basically, you can see here, you just follow, and within 3 or 4 comparison operations, you will deduce which digit you got as the input in the MNIST. And it works. It's not as good as the latest DNNs, but it's pretty good. But do you understand that? I don't. Okay? So the fact you use decision trees by itself guarantees very little. Okay, so now let's sum up what explainable means. And remember, I promised you some practical tricks. I have to deliver on that and to finish ahead of time. So the people at DARPA said, okay, what does really explainability or interpretability means? So they classify the kinds of questions it really embodies. So one is understanding why. And that falls under causality analysis or pattern discovery. The IBM session yesterday was very good in covering some of that. So basically, sometimes if it's an image, you can show there's a small part of the image, which if you take out or change, the prediction changes. So that's the reason. So causality means a very small, preferably subset of the whole input, which affects the result greatly. Pattern discovery is actually a good thing. You're trying to see, maybe the AI discovered some patterns you never thought about, like in biology, and that's great. The other kind of thing you want to do is knowing when it will succeed, okay? Like reliability, confidence for the output, okay? Which some people call reliability, and some people recently started calling abstention, from I abstain, okay? And that's actually the first very useful thing to have, right? People are going to continue deploying ML and AI because they work great. Wouldn't it be wonderful to have something which tells you, this time, don't use the AI. We're not saying it's wrong, but it's not sure, right? Just like when you use a substitute, you don't have your expert, and you have, what are physicians always told when they start? If you're not sure, talk to someone who knows more, right? So even by not making the model better, but even making the model able to raise a flag and say, I'm not sure, you can actually gain a lot, and I strongly recommend you consider that when applying ML, okay? Usually, in decisions of gravity, you are replacing people. You are not automating something which was already automated. You're replacing people. It could be brokers, it could be financial advisors, it could be physicians. So they're still going to be around. So if you have a mechanism to find when you don't trust your AI to overload this decision to them, that's great. Last, but that's the golden fleece, okay, is if you know, when people say, I want an explanation, when you come with your car to your car mechanic after it broke down, you don't really want an explanation, right? Maybe you want an explanation for the high bill, but really what you want is you want it to fix it, right? And that's what customers want. They come to you, point their fingers and say, you see this example? You made a mistake here, buddy. Your software is not good. And they expect you to fix it because that's what you do when you have software bugs. Only it's harder in AI. Can you do it? In some cases, yes, I'll show that as well. These are the two things I'm going to show. Okay, So causality analysis, I'm not going to discuss again because it's been discussed in other sessions and I don't have anything new to say here. I'll just give an example. So causality is finding, for example, regions in the image or words in the text that are the ones that caused you to think that your classification is X or Y. These are the key words or the key parts of the image. And there's excellent research on that. And there's going to be a good talk tomorrow as well, or two. Now let's talk about how to do abstention or reliability. So the trivial thing, if you open the textbooks, the trivial thing many people will tell you is use the threshold, right? If you have a classifier that's supposed to give a number between 0 and 1 for a class, it doesn't really give you a 0 or a 1. It gives you some floating point number in the middle, right? So basically they would say, okay, so if 1 means that's the class, then if it's below 0.8 or 0.7 or 0.5, don't use it. It's not ridiculous, but in many modern DNN networks, and you're welcome to try it, it just doesn't work well. Meaning you look at the actual errors you made, and when the mark of the threshold was below the threshold, and you will not find a strong correlation. And I'm not even sure I understand why, but I guess the answer should be why should it work? I mean, although people used a lot of Bayesian terminology to explain how networks behave, there's no a priori reason why the value the network outputs should be a measure of the confidence. There isn't. Okay. The second one, okay, here I made it into a drawing because it's math, but it's not complex math. People here who may use any kind of deep learning networks for NLP or for image, before the last layer, which is the classification, you almost always have a large, fully connected network, fully connected layer, right? Which is much bigger than the final one. So for example, if it would be ImageNet or face recognition or object recognition, you may have 500 classes or 200 classes, which will be the last layer, which is boring because that layer is really your output. And the layer before would be much heavier. Okay? We usually don't look at that layer. And we're saying it's worthwhile to look at that layer. What we did is we said, okay, let's run a network that's doing a classify. Let's look at this layer. It's just a vector of numbers. Okay? Now we have all our labeled past cases where we know the answer a priori. If some of them look very similar in terms of the vector, the actual numbers, the Euclidean distance, the Euler distance, doesn't matter, the Chebyshev distance, if they're very similar, then maybe these cases are similar. Maybe it's similar to a case that we've had in the past. And as another criteria, if let's say we have a new case and we get this vector, and this vector is very close to 2 or 3 past labeled vectors, but they belong to different classes. Okay, they're not, so we thought that's an A, or the network said that's an A, but the vector you get here looks a lot like an A, or like an 8, or like a B when you look at your training data. Then maybe that's a good sign you don't know what's going on. This image is different from the ones you had. So you can be, saying, my AI is so great, it will say what it is, and you can say, I abstain. I'm just not going to say why, because it's not similar to things I've had in the past. And it turns out that works well. We've had a team, one of them now works at Google, who did something similar, and they said, don't just look at the last layer, but look at a few layers below. They had a more complete formalism, but I'm not sure it gave better results, but it may. Anyway, we both had the same concept. Don't look just at the classification result. Look at what happens in the layers before and compare that to the labeled cases. That's the key thing, okay? And what they have shown is that this is wonderful, for example, for detecting adversarial attacks. Meaning, if you inject adversarial attacks, I remind you, is where you actually crafted an example which looks like something quite simple, but manages somehow to fool the network. So when they looked at adversarial examples, they found out they'd never behave like the normal ones. Okay, that's a very good way to filter 95, 98% of them. And it's very hard to make an adversarial example which will look like a regular sample when you follow it through all. If any of you are not sure how this is done mathematically or want to know more, come to me after. That's great. Okay. So then we went further and you said, okay, let's look at these past labeled cases, because for example for physicians that's a great thing. Physicians are like judges. They don't like to innovate. They like to say, I made the decision because well, it's just exactly like the case we had 3 months ago, or just like the case in the book. Okay, look, it's the same. So we said, okay, can we use this to retrieve past cases which are similar, and this will solve the case. This is the perfect explanation, by the way. There is no better way to explain. If the AI says, You see this picture? Well, you had one just like 3 months ago, and you said it's malignant. It's perfect, right? Because the physician then says, that's why I'm making that. And if the previous decision was wrong, well, what can I do? I mean, like, that's what people said. However, technically, it's hard when you have something like MNIST or ImageNet with tens of thousands of examples, you will find some pretty similar ones. But when you talk about other cases, they're just not that similar. The network thinks they're similar, ergo the one before last layer is very similar in the response, but to the human eye, it doesn't look very similar. So we said, okay, can we push it a little further? It's not a complete solution. We can't make one panda bear transform into another. But can we apply some continuous transformation that will take the previous labeled case and show it's like the new one? I'm sure you've all seen these movies like where they take a morph, the face of a person, and it morphs into the evil twin or something like that. That's what I'm talking about. If we could find a past case that was already labeled, and it's quite similar to the current one, and we can transform between them smoothly, that's a pretty good explanation. So first, I'll show how it's done. Okay? So these animations really start. The first frame, MNIST is, I mean, I could start with the medical images, but I'm not sure they would make a whole lot of sense. It takes a while until you get used to them. Digits are simple. We all know digits, right? So the first frame is the instance that we found right now, that we have to label. The last instance, the last frame in the animation is a pre-labeled example, and you see the transform. So basically what we're saying is if someone tells you, why did you think that's a 4? We say, look, there's been a previous case, and you just transform it like that. It's a 4 all along the way, and that's why we think it's a 4. Do you agree or disagree? Most of the time, if you did your transformation right, that's complete explanation. Sometimes, however, and that's the good part, you find things you never thought about. Okay? You didn't think about it, the customer didn't think about it. Look below. The one on the right is a 1. The one on the left is a 7. What is the one in the middle? I'm not sure. And it's not my job to make the decision. The point is, when you make this explanation, the customer has to say, okay, about the middle one, well, you have a point, I see. And then, it's not like it's the end of the game. It's not just that you explained and the customer says, okay, well, I'll take it, what can I do? They can then define whether they want this to be a 7 or a 1 or an abstention example. They may want to say, this area, things that look like that, I want you to raise a flag. I don't want you to make a decision, okay? There's one thing I always ask, when we give the courses, I ask people, MNIST has 10 classes, right? 10 digits. What's the missing class? And can you guess? I mean, there's something obviously missing in MNIST the way it's defined, regardless of the network. Well, if I show it now a picture of a house or a face, will a person say it's a digit? No. They'll say it's the 11th class, which I don't know about, right? That's a very important class. By the way, why don't we train for this class? Because it's bloody impossible. No one knows how to do that. The dark space, the dark matter of the unclassified, unidentified examples is what's always below, okay? But, okay, to show this a little graphically now, what I'm saying is in order to improve your model, remember that's the second thing I said. The first one will be when to abstain, and therefore improve your performance when you are sure. The second one is what to do now in your model. So let's make, we always do 2D because that's the simplest. So what we're trying to say is, what you really want in terms of more examples, you don't want more red or blue or green dots in the middle. These are the boring examples. The network already figured those out, right? You don't need any help there. It doesn't need help. You can add 1 million more examples. It won't improve your numbers. What you really want are the edge cases, okay? But you only have so many. However, when you do those transformations I mentioned, the smooth transformations, you are effectively creating new samples, okay? So if you had 4 digits and they're near the interesting area where you sometimes make mistakes, because if they're in the middle and you're always right, you don't care, then you can interpolate between them and make more examples and the boundaries, okay? By the way, this also, as you may know, while I'm talking about images, people are using now for speech recognition, they're actually converting into images. For genome, they're converting into images. So it's not necessarily just for things which started out as images, okay? Now, just to make it all a little more tangible, when we say transformation, it's not any transformation. For example, the one above is just, we started with 1, 4, we went to the other, and we just averaged them out, okay, with a rolling average. That's not a good transformation. at all. Why? Because in the middle, there are things which are not a digit. Remember, that's the 11th class. You don't want that, okay? Below, you have a good transformation. It took a 4, and it transformed it, squished it, smashed it into another 4, and all along the way, it was a 4. These are the kinds of transformations you want. But where will we find such an exotic creature? Well, actually, physicians have had to do it for a long time. Why? Because when they image body parts, they're semi-fluid, okay? They're not rigid, and the heart, for example, you can see the heart moves, and they've had for a while to do deformable image registration automatically between images which are sort of similar, but not the same. So there's plenty of methods. I mentioned one here. The guys in this method actually started by training it on MNIST just to see that the method works, but then they went on to try to use it on real, serious stuff, okay? But there's plenty of methods. The point is there's a body of boxes, black boxes or white boxes, but complex ones that you can use. So that's what we're using. So now just to do one example end to end, okay? And we'll finish with that. Let's say, and that's a real example. You built a DNN classifier for MNIST. It's really good. And this one is a 0. I don't make the rules. That's what the classification said. Not the network, but the original labeled data. And the customer insists, I want this to be a 0, not a 6. The nearest one we could find is this one, which was labeled as a 0, okay? So now I have to get from this to here. They're not the same. They may not look very different to you, but trust me, these are exactly the differences which make a difference in the classification. So here's the transformation. Below, just for the more mathematically inclined, if you look at the number of activations on the one before last FC network, you can see they get more similar to the right-hand side. The vector gets more similar to the labeled image as you move, or to the original image, okay? Which just shows that our transformation not only kept visually continuity, but also in terms of the network, it kept the continuity. So we were good in that case. Now you take all these middle cases and you put them back in the training, and it does wonders, okay? What you might have done before, and you can still try that, is just take the bad example and say, okay, I'll put it into the training and give it a big weight and say, you gotta learn this, you gotta learn this. That stops working at some point, very early on, for various reasons I don't have time to describe. Here, you just add these 10 examples because you actually gave it a path. It's like you gave the system, the AI, a guide. It actually converges very nicely, and it doesn't repeat the mistake. And another example, let's go back to the 7 or a 1, okay? What you really want there from the customer is you can define an exclusion zone. That's perfectly okay. You can say, the area on the left, that's a 7. That part of the path, these are all 7 examples. Please retrain on them. The ones on the right are 1 examples. The ones on the middle, just raise your hand or say it's like that case we had which we didn't like, because we're not sure what it is. So you can also define zones of exclusion. Just to show you it's not all about digits, this is a very important problem, which is classifying, segmenting blood vessels in the retina. In the UK, for example, about 3 million, I know the number because we're doing a project with the PHE right now. So there's 3 million diabetics, and basically the recommendation of your government, and rightfully so, is that if you're a diabetic and you're over 14, you should undergo yearly screening of DR, diabetic retinopathy, which is something which most of even diabetics will not get, but if you do get it, it's really bad, okay? And if you identify it in the early stages, you can actually do a lot about it, at least for most people. So part of that is you have to classify the blood vessels. So a blood vessel may seem easy to classify, but it's not, okay? You can see on the left a set of 3 networks doing segmentation with the cutting edge stuff. And they actually do a good job. You can see all the white places are areas where all the networks agreed. That's a good sign, right? But on the left, you see zoomed 2 parts. One, where in the middle, they stopped seeing the blood vessel. Okay, so it looks like it's torn, but it's not torn. It's really there, okay? And they saw some tiny part of a blood vessel where there is nothing is. So it seems like, okay, the network is really stupid, right? I mean, but you see, it's not so simple. When you zoom in into the original image, our eyes, people who've done, aerial reconnaissance or looked at asteroids or things, we already know that. Our eye can play tricks on us. When you actually zoom it to the information the network has, it's not so easy to decide, okay? our eyes are very good at building models. After 2 or 3 examples, a training ophthalmologist will learn that, okay, blood vessels are continuous. That's what they do. They transfer blood. Okay, they're not fractals. Okay, so in this area, if you look at the lower part and the upper part, so the lower part, I think everyone will agree there's a line there. On the upper part, our eye sees it, but if the network doesn't have this rule, it's not so easy to train it. Okay, so I'll skip this and I'll skip this. Okay, and I'll just show you this. Without further ado, you do the procedure I described before, which is taking the labeled example sets. In this case, the labeled input would be patches of retinal images, which were manually labeled, segmented by an ophthalmologist. Okay, there's plenty of those. And for each, what you see here as white is we took a new image, and wherever a patch in the new image resembled sufficiently a labeled patch somewhere so that we could transform one to the other continuously, then we said it's white. And where we couldn't do that, it's purple. So we maliciously injected digits which have no place in your retinal scan unless you're a cyborg. Okay, so it may be a tough realization to discover it first time you undergo. So digits, in terms of thickness, in terms of shape, they're not that much unlike blood vessels, but they are not blood vessels. They are not continuous, they form loops, they do all kinds of things. And the network said, you know what? I couldn't find anything which looks like it in my data set, even with transformation, so I'm not sure what it is. And that's exactly what we wanted it to do. Some people, some people might say, okay, that's really good if what you have to do is small graphical things, but if you have to recognize something like a whole human body, okay, a person walking in the street, to say it's a person and not a car or a mannequin or something, that does require some higher level thing. There is no easy way, even with medical transformation, to transform one pose of a person to another. It's not easy. But people are composed of parts as well, right? We have hands, we have feet, we have a chest, we have a head. And each one of those at low resolution is small enough that you can apply those methods to. So once you have an ensemble of recognizers that can recognize candidates for an arm, candidates for a leg, candidates for a chest, candidates for a head, then you can apply higher level network to say, if you have all these components in this relation, it's probably a human. And of course, if you want to discover, detect suspected cancer, pulmonary nodules in a chest, then rather than say you've got cancer or not, what you really want is to pinpoint these small patches and say, this one might be cancerous, this one might be cancerous. And then that's your explanation, right? You have a reason why you thought that. Maybe the physician will disagree with some of your findings and say, you know, append your decision. That's okay, but the flow is clear. Just another good way of showing explainability to customers. Here, we have something we claim may be something, and then we show them the 3D so they can see whether it's really a distinct nodule, which this one is not. It's just a blood vessel. I'm already half an expert. I charge much less than the NHS. You can come to me. Okay. And other examples, which they take, we show this in the 3D. And actually, you see, it's just sitting there, like an asteroid or something. That's a pulmonary nodule. It doesn't mean it's cancerous, but it's a nodule. Okay. Last but not least, just to leave off with a nice feeling and ahead of time, sometimes you have to apply an eye in space. Falcon 2, Hayabusa is Japanese for falcon, is just starting to return from an asteroid 1 light year away from it. It was 5 years in the journey. It took the samples, we can see soon, and it's starting to return. And when you're 1 light year ahead from it, you have to have some basically out. 5 probes on the surface, including shooting bullets into projectiles into the asteroid. Let's just hope if all goes well, we'll be back home. Let's hope the AI doesn't fail. Built by NEC. Thank you very much.